Earth is often called the water planet because of the abundance of liquid water on the surface, and because water's unique combination of physical and chemical properties is central to the dynamics of the Earth. These properties include water's exceptional capacity to absorb and store and release large amounts of energy as it changes state. Now, in the water beaker boil experiment, we took water from being a liquid to a gas by adding heat. And here you can see that this pot was sitting on some type of heating mechanism which caused the water to turn from a liquid into a gas. Now, if we were to actually look at the molecules that are inside of a solid, inside of a liquid, and inside of a gas, we can see how a water molecule is always going to be the exact same. Now, H2 means that we have two hydrogen molecules and hydrogen atoms in every molecule of water, and there's two hydrogen. There's only one oxygen. Now, oxygen is much larger than hydrogens, so when we draw a water molecule, it would look something like this, where this larger atom would be the oxygen, and then there's two hydrogen atoms that are attached, which makes this whole thing right here a water molecule. Two hydrogens and one oxygen. Now, if we were to just look at that molecule, if I were to represent the molecule with a circle, let's see what a solid water in the solid state would look like if we look at the molecules. So we're going to see just a bunch of molecules here stacked together, and they're going to have a specific shape because it's a solid. And actually, there's some vibration of these atoms as well. So I'm going to draw some little lines here to show the molecules are actually vibrating a little bit, but they don't have a lot of motion. Now, if we look at the water molecules in a liquid, they're going to be taking up the shape of the container. Now, in reality, all of the water molecules would be the same size here, but some of my circles are different sizes, so I can show that the molecules are really filling the shape of this container. So it's going to just fill the bottom of my box here if I were to pour water into the box. And these water molecules are going to have quite a bit more energy. So they're going to be having a lot more of a vibrational frequency around them. So I'll add some more of those lines. And as you can imagine, in a gas, water molecules are going to be bouncing all around. They're going to be flying around, and this is when we have steam. We actually see these water molecules go from that liquid state to the gas state as they fly out of that pan or pot and they enter the atmosphere. Now, water has some unique properties, like, for example, water can actually transmit light so that when light enters the surface of water, it doesn't stop there, but it can actually go down deeper, and it feeds some of those plants that are in the bottom of our lakes and rivers and oceans. It also has a really unique property that it expands when it freezes. So you can see here this ice mountain water jug. The top has come off because of the force of water expanding. So when all the molecules are in the liquid state and they fill a container, they have to stack in a very specific shape when they form a solid, and so it actually expands in space, and that's not true of all molecules, so it's unique in that way. It can also dissolve materials, as you may have seen before if you've ever mixed salt with water or sugar with water, like when you make Kool-Aid. That's water's ability to dissolve those types of minerals actually means that out in nature, water can transport minerals down streams, and then we can have minerals collect in our lakes and rivers. And actually, this is why the ocean is salty, because of all the minerals that have been transported down our rivers into our oceans, because all water ends up in the ocean at some point in time. Now, water can actually also get trapped here in the crust as it gets subducted, which we'll learn more about plate tectonics, but as that water actually is in that subducting crust, it has the ability to actually trigger melting in this region of the Earth's surface. And when that water is mixed with the rock, it changes the melting temperature of the rock rises up, and it creates these things that we call volcanoes. So you can see water has a lot of roles here on our planet, from feeding our plants in our oceans and rivers, to transporting minerals, to actually building our volcanoes and whatnot. Each of these properties plays a role in how water affects our Earth systems and other Earth systems. So ice expanding can contribute to rock erosions because it can help break rocks up into little pieces. And then the ability for ocean water to actually hold heat or let go of heat helps moderate temperatures. And that's something that we'll learn in our next unit. Now, water is found almost everywhere on Earth. From high up in the atmosphere, in the upper layers of the atmosphere as ice crystals, to lower down in like the troposphere, where we actually get clouds forming. So clouds are just water, but in the form of a gas. And it's these gases that form, that attach to little pieces of things in the air that we call condensation nuclei. So the dust particles and the pieces of space dust that are in our atmosphere allow water to attach to those and then build up the clouds that we have. Another thing that contributes to that is the amount of pressure that's in the atmosphere, and also the temperature of the atmosphere. So as you look further down in the atmosphere, sometimes you even see water forming, or we see water in the liquid state in our oceans, lakes, and rivers, or in the solid state, like if this mountain here had an ice cap on it, and we call those our glaciers. So you can see here that this is a mountain that is called K2, and even though this doesn't quite look like it, these are rivers of ice that are forming, and these rivers of ice are constantly eroding these surfaces of the mountains on the sides and digging deeper and deeper trenches. So if we were to melt all of the ice on our planet, we would end up finding some massive valleys in these regions. But this is in the Karakoram in the Himalayas of the Tibetan region, and these are rivers of ice. Now, energy from the sun and the force of gravity are what drive the continual water cycle among all these different reservoirs, whether it's the clouds in the sky, to our rivers and lakes, to the actual snow melt, or the glaciers that are running down our mountains. So sunlight is what causes or provides the energy that then causes water to evaporate. Once the water evaporates, it condenses. It was as a gas, but then it becomes this condensated type of water that we then call a cloud. And as the clouds continue to condense more and more water in our atmosphere, they build up and they get bigger and bigger and bigger, and they store more and more energy and more water until eventually we end up getting something called precipitation. And that can mean that we have some snowflakes falling, or we have some rain dropping, or we have some hail that forms as well. Those are all examples of types of precipitation. Once it precipitates, let's see, that's number 6. Let's find number 7 is that it's deposited. So if it's deposited as snow, it kind of stays there. If it's not deposited as snow, it actually starts to run off of the mountain in the form of a river. The river then comes to our lakes, and it's collected in our lakes. And at that point in time, some of the water actually goes down into the soil, and we have what's down here that we call our groundwater. Now, groundwater basically is just areas of our soil that, since we have openings of air between little tiny pieces of soil particles, we can actually store water underground. That water flows actually and can enter rivers and lakes and oceans even. So about 97% of our water, of our Earth's water, is in the ocean. But most fresh water, the stuff that we can drink, is going to be contained in glaciers. So that's going to be up in our highlands or our high altitude regions. And we have a few of those in the United States, a lot up in Alaska and a lot in the Himalaya. Also on the northern and southern caps of our Earth, it stays cold enough in those regions that we also have some of those glaciers and solid water that's stored on our Earth. It's also stored in these underground aquifers, and an underground aquifer is just a region of our groundwater that is really good at storing water. It's got the right type of soil. So you can imagine sometimes water plus soil equals mud, sometimes water plus soil can be like a sandy beach where the waters can easily move right through the soil grains. So those areas end up creating our underground aquifers. Water can also naturally come up in springs, and that's an area where water is coming to the surface of the earth, or it can come to the surface of the earth in rivers, or sometimes humans will use some wells, and these wells actually drill down in the surface and allow water to rise up to the place where the well has been drilled. Only a tiny fraction of Earth's water is actually found in streams, lakes, and rivers. Again, most is found in underground aquifers or in glaciers. But for our unit here on meteorology, we're going to be focusing on how water moves through our atmosphere, why clouds form, and then why we get different types of precipitation. So our actual next generation science standard that we're trying to learn right now is that we're working towards is ESS 2-5. So we need to collect data to provide evidence for how the motions and complex interactions of air masses cause changes in weather conditions. So essentially, we need to really focus on how air masses or masses of water flow from high pressure to low pressure, which cause this stuff that we call weather. Now, weather means that we're measuring the temperature, the pressure, the humidity, the precipitation that falls, and the wind speed, and that's at one location over time. So the weather can be different in Fort Collins as it is in Loveland. So it's important that we define where we're looking at when we talk about weather. And it's also important to remember that these patterns are really complex as far as when we try to measure how water moves throughout our atmosphere. And some things that can affect that is the winds that are on our planet, the landforms like mountains, valleys, but even the temperatures of the ocean water causes the air temperature to change too. And currents of ocean water can also be a factor. Now, one last thing is that weather can only be predicted in using probabilities because it is so complex. So we're going to be looking for some patterns, but by no means at the end of this will we be meteorologists, but it'll at least give us a taste of how we can at least kind of use some information to understand why clouds form, why precipitation falls, and we might even be able to use this in our day-to-day life to know if we should pack a raincoat, a short sleeve, or a long sleeve shirt in our backpack when we head out to go for a hike.